Assalamualaikum warahmatullahi wabarakatuh. Today we are going to present to you guys about microprocessor system lab 2 question 4. So before we continue our discussion about question 4, let me introduce you our group members. First of all, Arif bin Harun. Next is myself, Muhammad Rizaikan bin Zakairi, and lastly Ahmad Nurabani bin Sa'ayan. Next, we are going through to the objectives of this question.
So let's move on to the objective. The first objective of this project is to design and implement an ARM v7 assembly language programming on CPU virtual hardware platform. This allows us to apply assembly programming computer concept in a simulated embedded system environment. The second objective is to control a 7-segment display using a memory mapped input-output pooling technique with switches switch 0 and switch 4. The switches act as input while the 7-segment display serves as the output device. The third objective is to practice the important embedded system programming concept such as bit masking, branching routine, loop control and subroutine implementation. These concepts are essential for developing efficiency hardware interfacing program using an ARM assembly language.
Right now, I will explain about the result in our program. This program controls the Hexo 7-segment display using slider switch as input. First, when there is no switch being activated or being turned on, the system will remain in idle state. In this condition, the Hexo display continuously shows the letter S, indicating that the system is waiting for the user to insert the input. Next, when the switch 0 is being turned on, the program exits the idle state and enters the count up routine. The display shows numbers from 0 to 9 sequentially. A software delay is inserted between each number so that the counting process can be observed clearly on the 7-segment display. Next, when the switch 4 is being turned on, the program will execute the countdown. So, the 7-segment display will show a numbers that begin with 9 and will count until 0, with the same delay applied between each digit. Overall, the result confirms that the system successfully detect switch input, display the correct 7-segment pattern, and perform both ascending and descending counting operation according to the selected switch input.
So this is the flowchart. The program begins at the start block that initializes the memory address required for the hardware device. So the register R0 is assigned to the switch input address, which is 0FF20040, while register R1 is assigned to the H07 segment display, which is 0FF20020. Now, the flowchart moves to the program enters an infinite loop and continuously reading the current switch's status. The switch value is sorted in register R4. The first decision that's need to check is switch 0 is active. The program uses a bit masking operation to isolate bit 0 and compare its value. If switch 0 is on, the program branches start to count out routine. In the count out routine, the program accesses the data pool that contains 7-segment codes from 0 to 9. Starting from 0, each value is displayed on H0 one at a time and have a delay. After displaying a digit, the program cells are paused before moving to the next number. This process continues until it reaches 9, from 0 to 9. Let's move on to if switch 0 is not active. The program proceeds to the second decision, which is switch 4. It is similar to the previous, but if switch 4 is on, the program branches its countdown routine. In this routine, the program starts from 9 and display each number in descending order until it reaches 0. Also, it have a delay inserted between each number. If neither switch 0 or switch 4 is active, the program executes the default operation by displaying the character S on the 7-segment display. After completing any operation, whether the counting up or counting down, displaying S, the program returns to the main loop and continuously monitor the switches for any changes. This allows the system to respond immediately whether the user active a switch. Overall, the flowchart demonstrates how the program uses memory input and output decision.
Next, I will explain about this slide. This slide shows the 7-segment display encoding table used in our project. A 7-segment display consists of 7 LEDs labeled A, B, C, D, E, F, and G. Different combinations of these segments are turned on to form a numeric digit 0 until 9. In the table, D0 until D6 represent the control bits for each segment. A value of 1 means the segment is activated, while 0 means it is being turned off. The final column shows the hexadecimal value corresponding to each digit pattern. For example, to display digit 0, all segments must be turned on except segment G. This produces the hexadecimal value 0 times 3F. To display digit 1, only segment B and C are being activated, producing the hexadecimal value 0 times 06. These hexadecimal values are stored in array within assembly program. During execution, the processor reads the appropriate value from the array and writes it into the hexo display register. As a result, correct digit will be appear on the 7-segment display. This encoding table is important because it acts as a reference that convert numeric value into the 7-segment pattern required by the hardware display. Without these hexadecimal codes, the processor would not know which segments needs to be illuminated to form each digit that we need. So right now, I will be explaining about input and output, or before and after. So the input will be the switch and the output will be the numbers that will be displayed on the segment board. So on condition 1, which is no switch being turned on or the system on idle mode, so switch 0 until 9 will be remain 0 and the output will be 0, 1, 1, 0, 1, 1, 0, 1, or number 5, which is 0 times 6D, the hexadecimal number. So the output will be number 5 that will be displayed on the 7-segment board. On condition 2, which is as switch 0 been pressed, so the input at S0 will be 1 and the output will be displayed as 0 times 3F, 0x06, 0x5B, 0x4F, 0x66, 0x6D, 0x7D, 0x07, 0x7F, 0x6F. So the numbers will be displayed is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 on the 7-segment board. So this is show the countdown from 0 till 9 or countdown upwards. Then I will show you the condition 3, which is switch 4 will be turned on. So the output will be 0x6F, 0x7F, 0x0F, 0x7D, 0x6D, 0x66, 0x4F, 0x5B, 0x06, 0x3F. The numbers that will be displayed on the 7-segment board is 9, 8, 7, 6, 5, 4, 3, 2, 1. This is show a countdown downwards. So this is what the input and output that we will get based on our operations.
Now I will explain about the coding of our question number 4. So from line 1 until 5, we begin at the start level. These first 2 lines load our physical peripheral address using PC relative literal pools. Then for line number 4, register R0 points directly to the base address of our input slider switches, while at the line 5, register R1 points to the 7 segment display control register. Next, for line 7 until 9, we enter our main pulling loop label ulang. Here, we load the raw status bytes of all physical switches into register R4 using a memory read operation. Next, line 11 until 13, we check our first condition. We isolate the first very switch bit, switch 0, by applying a logical AND mask. If the result equals 1, it means switch 0 turned on, and the program immediately branches to our ascending counter routine label hitung naik. Next, line 15 until 17, if switch 0 was not active, we evaluate the next condition. We bit mask register R4 with hexadecimal value 0x10 to target switch 4. If switch 4 is high, the processor redirects execution to the descending counter routine named hitung turun. Next, from line 20 until line 22, if neither switch is turned on, we fall into our fallback state, default state. We move the active high pattern 0x6D into register R6, which creates the letter character S on the 7 segment module. We write this out to our display using a store command and branch back to ulang. Continuously watch the inputs. Next, from line 24 until line 27, when switch 0 is triggered, we step into hitung naik. We use the PC relative address instruction ADR to dynamically load our raw segment binary table into register R2. Then, we reset our tracker index register R3 to 0. Next, from line 29 until 33, inside the naik loop, we read an exact single byte pattern from our data pool using base plus offset address indexing. We push this pattern out to change the numbers showing on the hexa 0 terminal, and then perform a branch with link jump to execute our time delay subroutine. Next, from line 35 until 38, after returning from our brief pause, we increment our index register by 1. We test if our tracker has reached 10, which means we have finished displaying digit 9. If the index is less than 10, it branches backwards to repeat. If it finished, it jumps back to the main switch monitoring loop. Next, from line 40 until 43, if switch 4 is active, we trigger hitung turun. We grab our data array pointer and preload our loop index register R3 directly with the number 9 to handle a backward sequence. Next, from line 45 until 49, we load the index target byte into register R6, write it straight to the screen and call our visual pause function. Next, from line 51 until 53, we then subtract 1 from our array index and automatically update our condition flags. As long as our index number remains greater than or equal to 0, the countdown sequence repeats. When it finishes, we jump safely back to ulang. And next, from line 55 until 62, to prevent the numbers from changing too fast for the human eye, we have our delay subroutine. We have field register R7 with a loop parameter constant. The inner label lagi subtracts 1 from this register continuously until it reaches 0. Once complete, BXLR shifts control back to our calling loop. And lastly, from line 64 until 67, finally, at the bottom of our text space, we store our inline byte values for active high patterns directive terminates compiling cleanly. This concludes my explanation of the program logic. Next, we go to simulation.
I will explain about the simulation demonstration. For the simulation, the program was executed using CPU ladder. The slider switch were used as an input device, and the Hexo 7-segment display was used as an output device. Initially, all switches were set to off. During this state, the Hexo display continuously showed the letter S, confirming that the system was operating in idle mode and waiting for the input from user. Next, when the switch 0 been turned on or been activated, the simulations show the display counting up from 0 until 9. Each numbers or digit that appear once at a time with a short delay, demonstrating that the count up routine and delay were functioning correctly. After that, switch 4 been activated or been on by the user, the display will be count down from 9 until 0. Verify that countdown routine was executed as intended. The simulation result matched the expected behavior of the program, confirming that the switch, detection, branching, introduction, delay routine, and 7-segment display control were implemented successfully.
In conclusion, this lab successfully demonstrates peripheral interaction using a bare metal ARM-V7 assembly environment. Through memory mapped input-output, the program is able to read, switch, input and control the 7-segment display effectively. The implementation correctly fulfills all the project requirements by performing both ascending and descending counting operation based on the selected switches. The use of bit masking, branching instruction loops, and subroutine enable accurate and efficiency control of the embedded system. Overall, this project has strengthened my understanding on ARM-V7 assembly programming and provide valuable hands-on experience on the hardware.